Okay, so I'm going to talk about something called difference quotient. And of course, you guys have started looking into differential calculus by now, uh, which is the next part of your syllabus. And let me just write this down. For differential calculus, you guys will be going through chapter 6, 7, and 8 from the book. Now, what we usually do is we treat chapter 6 more as sort of like an introduction. So, not even an introduction, sort of like a entryway into differential calculus. We don't really spend a lot of time behind it and spend half an hour, maybe 1 hour behind it, and then we move on to chapter 7 and 8, which is where we spend most of our time in Eco 201 for differential calculus. So the notes, the videos that you guys see in BUX will focus mostly on 7 and 8. So what I have decided to do is to create a very short video on chapter 6, which is difference quotient. And what that will do is sort of help you understand exactly what chapter 7 and 8 are about, because you will be seeing a lot of formulas, and these formulas are very easy to use. As I've said to you guys already, is that matrix is the toughest part of the syllabus, which we have done already. Differential calculus, there are a lot of formulas, and that may scare a lot of you, but uh, at the end of the day, it's just a lot of formulas, and if you can figure out which formula to apply in which situation, you will really have no problems. But the question a lot of you have is where exactly are these formulas coming from? How does the formulas make sense? Basically, you don't want to just memorize the formulas, you also want to understand why they apply. So that's what I'm going to try and do here and now, is try to give you guys some idea about how the formulas work. Okay, so suppose let's start with a diagram. We have this, we have x here, and we have fx here. So let me just draw this. Suppose this is what we have. This is a diagram. Now notice usually we would call this y, but as you all already should know, y is equal to fx, the way we write this down. So it's the same thing. And suppose we, at this initial point, we have x equal to a. A can be anything, 7, 8, 9, 10, doesn't matter. And therefore, what we will have here is fa. And now suppose we move on from this point to this point, this distance. And this distance, I'm going to use another ink. This distance is suppose length b. If that is length b, then what we have now, over here, x is equal to a plus b. That should make sense to all of you. And as a result, what we have here is f a plus b. Nothing different here, stuff you guys have already known. So what I'm going to do now is let's give them names. So let's suppose this is point P. Let's not use P. I mean, in economics, P tends to mean price. Let's call this point S and point T. Okay. Now, what we want to do is calculate the average change when we move from S to T. Okay. So at S, what we have is x equal to a and y equals to fa. And then we move to t. What we have is x equal to a plus b, y equals to f a plus b. And what we want to calculate, do you guys remember the formula for slope? Slope was basically change in y due to change in x, right? So that's what we're trying to calculate here as well. So suppose the slope of not a line, but right now we're trying to calculate the slope between s and t. Okay. So what that will be is effectively changing y. So changing y over here is this when we're moving from FA to FB. Let me just write down this formula, change in y divided by change in x. I remember that the triangle, this is known as delta. This means change. So change in y divided by change in x can be given by the formula. What's the change in y? The new value of y minus the old value of y, right? That's the formula. And what is change in x? The new value of x minus the old value of x. So what we end up with is minus fa divided by, notice here a and a cancels out. So we are only focused on the change. We move from a to a plus b, so the difference is b. And so this is our formula. We have it right now. So let's, if we wanted to do some practice, let's take a look at, let me just draw out another simple diagram. So we have x here, we have y here, or let's just call this fx, function of x. We have a line here. Doesn't have to be a straight line, as you all know. And so suppose we are starting off at this point where x is equal to 3. And when x is equal to 3, now let's write down a function. Suppose what we have is y equal to 3x squared plus 4. Just any random function, okay? And we start off at x equal to 3. So if x is equal to 3, and of course, notice that this is fx equal to, let me just write this down properly. So y effectively is equal to fx, which is equal to 3x squared plus, I don't remember, was it plus 4 or plus 5, doesn't matter. This is what we have. If we're starting off at x is equal to 3, and fx is equal to how much? 3, then this is 3 squared plus 4. So we get 9 plus 3, 27 plus 4, 31. So we have this. This here is 31. And from here, we move to, suppose, to 7. So we were here. Now we have moved here. This is 7. And when we are at x equal to 7, we of course have a new value here, and we have to calculate that as well. If x is equal to 7, fx equal to 3, x squared becomes 7 squared plus 4. Okay, so 7 squared is 49, times 3 is how much? 147, I suppose, plus 4 is 151. So we have 151. So let's summarize. We started off, let me give this numbers again. Let's call this is M, this is N. Okay. So where did we start off at? We started off at M, where we had x equal to 3 and y equals to 31. And then we've ended up at N, where x is equal to 7, y is equal to 151. Okay, so I've actually made a mistake, which is the diagram will not obviously look like this. Let me just redraw the diagram. Sorry if this is confusing any of you. So basically what we are going to have is something that looks like this. Okay. Now that should be fine. I'm sorry, I wasn't paying attention. So we started off at this point where x was equal to 3 and y was 31. And then we have moved on to this point where x is equal to 7 and y is equal to 150. And I had called these points M and N. Okay. Now suppose what we want to do here is find average change in y when we move from M to N. So basically, I mean, it should be pretty straightforward for you guys to understand what we're trying to do. We've moved from M to N, and as a result, the value of y has changed. Or another way to say this would be that the value of x has changed from 3 to 7, and as a result, the value of y or the value of fx has changed. We want to find the average change. Okay, so average change is calculated by the formula we have already seen, change in y divided by change in x. Okay, and so what was our formula? We had a plus b minus of a divided by b. Of course, we don't have a and b here anymore. What we do have, if a plus b in our case is f7, basically. That's where we had ended up in. And if a is f3, this is the original position, divided by the change in x. Remember, we had started off at a, then we had moved on to a plus b, so the change was b. In this case, we've started off at 3, we've moved on to 7, so the change is 4. And now we can do the calculation. If 7 we've calculated is 151, if 3 is 31 divided by 4, so we get 120 divided by 4, that's 30. So average change in y, this is between m and n, or we can write between f3 and f7 is 30. Okay, so what does this mean? What this means is that on average, 1 unit change in x between the range 3 and 7 will lead to a change of 30 in the value of fx. Now that 1 unit change can be from anywhere within the range. So between 3 and 7. So when we move from 3 and 4, when we move from 4 to 5, 5 to 6, 6 to 7, it doesn't even have to be a whole number. 3.75 to 4.75, 5.63 to 6.63. There's an infinite number of 1 unit changes that we can have between 3 and 7. And these different changes, may lead to different change in y, but on average, they will always lead, uh, they will lead to a change of 30. So this is the average value. And average value is fine for straight lines like this, because, for a straight line, the slope is not changing. So let me give you guys another example. Uh, suppose we're calculating inflation in a country, okay? So we have the year here, and we're calculating inflation. By how much is money increasing every year? And if this is what it looks like, see, there's not much fluctuation between points. So suppose this is 2018, this is 2019, this is 2020. So there is inflation, or a better way to call this would be price level. So what you see is there is definitely an upward trend, but there isn't a huge deviation between these points. And so we can use this average change for this purpose. The problem with using average change is when we have graphs such as this. So for another country, when we look at price level and year, suppose what we see is that their graph looks like this. And that can happen. There may be seasonal demand. Even in Bangladesh, in certain seasons, demand of goods and services really goes up. And then in certain years, demand for services goes. Certain seasons, demand for services goes down. For example, twice a year, during the two Eid periods, there is a surge in price level of goods and services, but then after the Eid, price levels come down again. So there can be fluctuations, there can be seasonal fluctuations. During summer months, let's say demands are very high, but during winter months, demands are low. And things can happen. So the problem then occurs is that suppose we measure inflation of 1 year here. Okay. So this is suppose 2018. And then we measure the inflation of 2019 here. If we calculate, this is price in 2018, this is price in 2019. Now, if we use the average change formula that we have seen, all that we are doing is we're taking this point, and we're calculating the average change of this line. Okay. So we are assuming this was the price in 2018, this was the price in 2019. So this is how the price has gone up, a linear straight line. And then we use average change and see what has been the average change every day or every week or every month, how much the price has gone up by. The big problem with using this method is that we get rid of all this, as you see, all these changes. Price has shot up, price has come down, price has gone up again, price has come down again. And if you're the government of a country and you're trying to regulate the economy, you're trying to devise policies that is going to stabilize the country and not lead to too much fluctuations, then using the average change in this case is not really useful, because as should be obvious to you, is that price has not changed in a linear fashion. There has been a lot of fluctuations. So what can be one solution to this? Uh, the solution is, from average change, we move on to something called the instantaneous change. Instantaneous change. So instead of looking at the average change between a range, in this example, looking at the average change between 2018 and 2019, what we can do is look at what the curve is doing, not in an interval, but at one specific point. What is the curve doing exactly at this point? What is the curve doing exactly at this point? What is the curve doing exactly at this point? That is what we want to calculate. Okay? Because at this point, what is the curve doing? It's going up. At this point, what is the curve doing? It's going down. And what we want to be able to do is calculate the rate at which the curve is going up or going down at one specific point, not over a range, because a range will always give us an average value between 2 points. So all we need to do to calculate instantaneous change is, well, this was our formula, change in y divided by change in x, fa plus b minus fa divided by b. What we are going to do is we are going to impose a limit, lim, and the limit is going to be that x is going to approach 0. Okay, so what does this mean? When we say x approaches 0, we're not saying x is equal to 0. Of course, if there is no change in x, there is no change in y. So effectively, this whole thing is 0. There's no change. We're not saying x is equal to 0. We're saying that the change in x is becoming smaller and smaller. It is as small as we need it to be. The change in x, change in x, sorry, change in x. Change in x is getting very close to being 0, but not quite. So effectively what we're saying is that there is going to be a very small, minuscule change in x. And due to this very small change in x, what is going to be the change in y? So if I were to draw this graphically, suppose this is what we have, and suppose we start off at this point and this point, and then there's going to be a very small change in x, a minuscule change in x, too difficult for me to draw here, it's so small. And as a result, there is also going to be a tiny minuscule change in y. But theoretically, what we are going to be able to do is calculate the rate of change, the average change of exactly this point. And that's the instantaneous change. Instead of average change that we had done before, we are going to be dealing with instantaneous change. So let me just bring down this formula again. This was 3x squared plus 4. Okay, let's deal with the same formula. So we had fx equals to 3x squared plus 4. Okay, and we want to calculate the instantaneous change. So let's do that. Okay, forgot to mention this formula right here. This is what's known as the difference quotient, or DQ for short. And this is what gives us the instantaneous change. So let's apply instantaneous change for this formula. Fx equals to 3x squared plus 4. Okay. So we are imposing a limit that change in x is approaching 0. Therefore, change in y, change in x is equal to, let's write down the formula. Okay. So fx, and we're moving from a to a plus b. So this formula becomes 3 a plus b squared plus 4. This is fa plus b. From this, we subtract fa. So 3a squared minus 4. This whole thing divided by 4. Okay. Let's see what happens. 4 and 4 cancels out. What we get is 3a squared plus 2ab plus b squared minus 3s squared divided by b. 3s squared plus 6ab plus 3b squared minus 3s squared divided by b. So 3a and 3a cancels out, and we have a b in the denominator. So what we, this and this cancels out. So we have 6a plus 3b. Okay, and so let's think about what this means. Before that, let me just write down the full thing. We have, if we just had change in y divided by change in x, this would be our answer. And if we plug in the values, now remember what was a and b. We had gone from 3 to 7 in our example. Remember, 3 to 7. So as a result, what we would have said was a is 3 and b is 4, because we're moving from 3 to 7. So the change is 4. So what would we get? 6a plus 3 times, this is 3. So what we get is 18 plus 12 equals to 20, is what we had already calculated. So this isn't anything new here. However, this is not what we have, is it? What we really have, this was the average change, and we have already calculated that. What we now have is also a limit, which says that change in x is very close to 0. Change in x is very close to 0, then this is not true. B is 0. Let me write it properly. We're starting off at point A, which is x is equal to 3. But from there, we're not moving very far. Look at this diagram. From x, we're moving to a new value of x, but we have assumed that change in x is very small. Very small, so let's just assume it's a negligible value. So effectively, what we end up with is 6, a is 3, plus 3 times, now over here we have a value that's not exactly 0, but very close to 0. So let's just assume that it is 0. And what we end up with is 18. What that means is that at specific point of A is equal to 3, not over a range like we had seen previously, but at the specific point of A is equal to 3. Let me draw this again right here. We have this fx here, we have fx here. This is A equal to 3. We have at this point A, at this specific point, we're not looking at a range. At the point A, this is what we have. That means that the curve, the slope of the curve at that specific point is 18. Not over a range is what we had done before, is that over this range of 3 and 7, what's happening in this range, or what's happening in this range. We're not looking at range anymore. Now we are looking at one specific point. And that's why this is called the instantaneous change. Now, a lot of you may be thinking, what does this have to do with differentiation? So let me explain that as well. So before doing that, I'll pause this video, and what I will ask you guys is to go to chapter 6, look at practice, the exercise 6.1, I suppose, the first one, and try to do a few problems from there. And you should all be able to do it now that you've seen the one example. Once you've done that, come back here and I will explain the difference, the similarities, or how the difference quotient is related to differentiation.